So yesterday, in the first Marshall lecture, I opened at the beginning by saying there were two things that made the incentive auction particularly challenging, and I focused on one of them yesterday, which was the extremely complex constraints on the channel assignments, and how that led us to develop a different approach to the reverse auction. We had to decide what set of stations to buy. Now, this assumes that we've already decided how many channels to clear. So the lecture yesterday wasn't about the actual incentive auction. The lecture yesterday was about, suppose that I've decided that I want to clear some number of channels, and I have only so many channels left to assign stations to. How should I do that, and how should I buy stations to take them off the air to achieve objectives that mix efficiency and cost and satisfying budget and so on. Okay, so that's what we covered yesterday. There were about 2,500 stations to put on the air. We had to balance efficiency and cost objectives. That was the topic of the first lecture. For the second lecture today, we're going to be talking about the second issue that's here, which is that this is actually a two-sided auction with heterogeneous items, and we have to decide how many channels to clear. And we had to do that uniformly. We had to decide how many channels to clear in a nationwide way so that the same channels were cleared in Los Angeles and New York and Chicago and so on, so that the whole network could be engineered to operate efficiently. And we had to do that in a way that respected a budget constraint. We had to take into account how much revenue we're generating in the so-called forward auction, where we were selling mobile broadband licenses, and what the cost was of acquiring spectrum in the reverse auction, where we were buying mobile television broadcast rights. Okay, and yesterday, as today, we had to keep the rules simple and understandable for bidders. I actually didn't talk a lot about some of the simplifications we decided to make, but we're trying to keep the rules simple and understandable for bidders for obvious reasons. Okay, now part of the reason for that I decided to specialize my lecture is I wanted to say something about Marshall in these lectures. These are the Marshall lectures. And Marshall did influence, or did have an idea that influenced our design. So this is a quote from Principles of Economics, 1890, from Chapter 3, Equilibrium of Normal Supply and Demand. And he wrote the following: when, therefore, the amount produced in a unit of time is such that the demand price is greater than the supply price. So what does that mean? So you have a supply curve and you have a demand curve, and you have a quantity. And for that quantity, whatever quantity you specified, you pick out the price on the supply curve, and you pick out the price on the demand curve. He says if we're producing a certain quantity, and if the demand price is greater than the supply price, then the sellers receive more than is sufficient to make it worth their while to bring goods to market to that amount. And there's an active force at work tending to increase the amount brought forward for sale. Okay? And what's more important for us is the next sentence, which is the reverse. On the other hand, when the amount produced is such that the demand price is less than the supply price, sellers receive less than is sufficient to make it worth their while to bring goods to the market on that scale, so that those who are just on the margin of doubt as to whether to go on producing are decided not to do so, and there's an active force at work tending to diminish the amount brought forward for sale. When the demand price is equal to the supply price, the amount produced has no tendency either to be increased or to be diminished. It is in equilibrium. This is a pretty famous passage, actually, for some of us who think about price adjustments. There's so-called Walrasian dynamics and so-called Marshallian dynamics. Walrasian dynamics is the idea that if you haven't found, if supply and demand are not in balance, if there's a price that prevails in the market, if at that price demand is greater than supply, then the price tends to increase. And if at that price demand is less than supply, the price tends to decrease. So it's price adjustment that drives things, and this is quantity adjustment driving things. And quantity adjustment is what we're going to do in the actual auction. So I want you to look at this again, and now I'm going to show you how the FCC describes what we did in the actual auction. So let's see if this will play for me.
How does the incentive auction work? First, a reverse auction determines how much it will cost to repurpose a given amount of spectrum previously licensed to television stations. TV stations are offered money to vacate their spectrum. Stations that do not sell are guaranteed a channel in their current frequency band. The reverse auction starts with high prices offered to TV stations. If more stations accept these prices than needed to clear the specified amount of spectrum, prices decrease. As prices drop, some stations will reject the prices offered and join the set of stations that will remain on the air. If no spectrum is available for a station, the price offered to the station stops decreasing. The auction continues until there is no spectrum left for any of the stations accepting the prices. This establishes the amount of money needed to clear the spectrum. Next, the same amount of spectrum is offered in a forward auction to wireless carriers. In the forward auction, prices start low and rise until the amount of spectrum for which there are bids equals the available supply. If the amount bid by wireless providers is not enough to pay the broadcasters, then the auction continues to a new stage, in which both the reverse and forward auctions are repeated starting where they left off. In each succeeding stage, the FCC designates a smaller amount of spectrum to be sold to wireless carriers, and therefore needs to buy fewer channels from TV stations. Because this frees up more space for TV stations, competition among TV broadcasters makes their prices go down. And then in the forward auction, less wireless spectrum for sale means more competition among wireless bidders, which increases the price of the spectrum. The incentive auction continues through as many stages as are necessary for money bid by wireless providers to pay the selling TV broadcasters. At that point, supply and demand are in balance and the auction ends.
Okay, so if you had just seen the previous account and then saw this, you'd say, gee, that looks a lot like Marshallian dynamics. And in fact, this was inspired by Marshallian dynamics, but we'll see it's not exactly the same thing. What they've said has gone on here is we start with a large quantity, and we start with a large quantity and we figure out how much it would cost to clear that quantity of spectrum. And then we take the mobile broadband licenses and we find out how much revenue we could get from selling those mobile broadband licenses. And if the revenues that we receive from sales is less than the cost of clearing the spectrum, then we reduce the quantities and continue. And again, because these are monotonic processes, what will happen is when we reduce the quantity, the price that will be offered in the forward auction will continue to rise, and the prices that will be charged in the reverse auction will continue to fall. And the hope is that at some point the revenue from the forward auction will exceed the cost from the reverse auction, and this all ends. And if this was a homogeneous product, this would be very much Marshallian dynamics. Okay? But it isn't a homogeneous product. So are these things which are, let me acknowledge to begin with, this whole process was inspired by Marshall's idea, but are they really the same thing? Okay, Marshall was writing about a single homogeneous product. And in that context, one of the things that happens with a single homogeneous product is if you are trying to clear a particular quantity, so we're going to have 100 units, and you find that some suppliers are not included in the solution for 100 units. If you then reduce the quantity to 90 units, the suppliers that you weren't using for 100 units, you're not going to use them for 90 units either. Okay, that's normal, intuitive. You might think that that was obvious and would hold in general, but you'd be wrong. In the incentive auction, we also had a single coordinating quantity, what we call the number of channels to be cleared, but they're not all the same thing. And the suppliers are all unique. And the way they fit together varies. And just to give you some idea of, I introduced the knapsack problem yesterday, so let me introduce that intuitively for you today. So imagine that we think of us as having a knapsack problem. We have some amount of space into which to put stations to continue broadcasting, but we don't know how big the knapsack is going to be. And if we can't afford to buy all the broadcasters we like, we have to put more broadcasters on the air. We have to make the knapsack bigger and buy fewer channels and fewer stations and put more back onto the air. So this is a knapsack problem, or like a knapsack problem, in which we don't know the size of the knapsack and keep making it bigger round by round. Now, if you imagine that you're trying to fill a knapsack and it has a particular size and you're using a greedy algorithm, what will happen in the knapsack problem is you'll put in the most valuable items, and then finally there's not going to be enough space for the stuff you'd like to put in. So you'd put in a bunch more little items and fill it up with the less valuable items that you could still fit into the knapsack. That's what would happen in a knapsack problem. And then suppose I come along and said, oh, well, actually, you have a bigger knapsack to use. You can stretch this a little bit. Well, now you've already stuck that junk into the knapsack that you might not have chosen otherwise. And now some of the more valuable stuff you don't have room for because you thought you were filling a smaller knapsack. So you get this, you have this problem where when we're packing TV stations, when we go through a series of rounds, it's at least conceptually possible that we'll pack some less valuable TV stations onto the air because we think there's no room for the more valuable ones. And then when we discover we have more space, we'll regret the decisions we've made earlier. That stations that we use to pack a small knapsack might not all be ones we want to use to pack a large knapsack. Now that might sound unlikely to you, but I'll show you. Okay, so let's move forward. And that raises the question, by the way, this is the quantitative question we want to ask. Can it be important that a supplier that's not valuable in clearing a high number of channels is valuable when we're clearing a lower number of channels? Okay? So in order to give you some sense of the mess that this problem is, I'm going to take you through how we were doing the spectrum clearing, and this will give you some sense of why this problem was more complicated than the problem that Marshall was looking at. And what I have here are different amounts of spectrum. The channels that are shown here are channels 21 to 50, some of which were involved in clearing in the auction. Channel 37 is different. It was reserved for radio telemetry and medical devices, and we were unable to put a broadcast television station on it or to put mobile broadband on it because we didn't want to interfere with existing medical devices and radio telescopes. So channel 37 is not available to us. And let's take a look, for example, at the bottom line of this table, which has a 126 next to it. The bottom line of the table it represents a situation in which we're going to try to clear 126 megahertz of spectrum. That each channel is 6 megahertz, so that's 21 channels are to be cleared. So you can see here that channels 21 to 28 are going to continue to be used for broadcast television, and everything from channel 29 to 50 is now being used for something else. And many of you don't know anything about the technology of mobile devices, but for these bands and through most of the bands that we use in Europe and North America, we use duplex technology. We have if band A has a part of the band that's reserved for uplink and a part of the band that's reserved for downlink. And these things can't be adjacent to each other or they would create interference within the device itself. If you're sending a signal from your device in this frequency and in the adjacent frequency you're receiving a signal, you can get radio interference between those uses. So we have a license for 10 megahertz of spectrum consists of a 5 megahertz uplink license and a 5 megahertz downlink license, which are split apart in the spectrum. Okay, that's just part of the engineering. And that's license A, and here's license B, and license C, and license D, and so on, each of them consisting of paired blocks of 5 megahertz of spectrum, 10 megahertz in all. And then in addition, because we can't have uplink and downlink next to each other, you'll notice there's an 11 megahertz guard band between the uplink portion of the spectrum and the downlink portion of the spectrum. We have to have some space between them that keeps them separate to avoid the kind of interference that I was describing. And then in addition to that, we have other guard bands. You can see that around channel 37, in order to prevent interference between other uses in channel 37, we have 3 megahertz of guard band at least on each side of channel 37. It has to be at least that. So over here, we had to use 6 megahertz. We had to use all of channel 36 because that's the size in which the stations come. Okay? Now, why am I showing you this detail? Okay, so this is all very detailed stuff. In order to clear 10 channels here, we need to clear 126 megahertz in order to create 10 licenses for sale, we need to clear 126 megahertz of spectrum. In order to create 9 licenses for sale, we need to clear 114 megahertz of spectrum. Here's a summary. 10 licenses require 21 channels. 9 licenses require 19 channels. 8 licenses require 18 channels, and 7 licenses require 14 channels. So let's look at those numbers for a minute let's look at those numbers for a minute. Suppose that we want to think of the cost of providing a mobile broadband license in terms of the number of channels it requires. And let's look at these marginal costs for a moment. So if we want to go from 7 licenses to 8 licenses, the cost of that is 4 channels. If we want to go from 8 licenses to 9 licenses, the marginal cost of that is 1 channel. If we want to go from 9 licenses to 10 licenses, the marginal cost of that is 2 channels. This is a very ugly pattern of marginal costs. Okay? It costs 4 times more to go from 7 to 8 than it costs to go from 8 to 9. This is a very ugly kind of pattern. And let's see, let me skip here for a moment and I'll come back to this to show you how this played out in the auction. But this is on a log scale, logs base 10. If you were to take a look at the number of channels cleared versus what it cost us to clear the channels, it looks very nice. It's on a nice linear scale, except that going from 10 licenses to 9 licenses to 8 licenses to 7 licenses, we have really quite a drastic drop in the cost because we have so many fewer channels to clear. So here's what it looked like from the standpoint of the stages in the auction. Okay, so what do we see? The first round of the auction, how did the government decide how much they wanted to clear? They set the highest possible clearing target. They took a look at the stations who were participating in the auction and said, if we could buy all of them, how much spectrum would we clear? Of course, they can't buy all of them. They're going to be really expensive, and there's not much competition then to set prices. It would have cost $86 billion to clear 10 channels. And the revenues, and that's what they started at as the target, the revenues in the forward auction were only $23 billion, small shortfall, okay? So stage 1 didn't work, and we move on to stage 2. We reduced the quantity. So instead of clearing 21 channels and creating 10 mobile licenses, we create 9 mobile licenses by clearing 19 channels, and the cost falls to $55 billion. And the revenues, prices rise a little bit, but the quantity has fallen, and the revenues fall to $22 billion. In the third round, the cost fell to $40 billion for 8 mobile licenses, for 18 of these, and the revenue was $20 billion. And finally, in the fourth round, when we got that big chunk of 4, that marginal 4 licenses, 4 channels out of the way, going from 8 licenses to 7, our costs fell from $40 to $10 billion, and the revenues fell from $20 to $19 billion. So we went from having a $20 billion deficit to having a $9 billion surplus. So this is hardly supply equals demand. We get to the point where revenues equals costs, right? This is very discrete, and sometimes the discrete jumps are enormous, right? We have this fall from 40 billion to 10 billion, and just going from 8 licenses to 7 licenses, we went from a $20 billion deficit to a $9 billion surplus in the course of the auction. So this looks a little bit different than Marshallian dynamics. First of all, because of because we don't come anywhere near to getting actual equality, unlike the nice graphic that the FCC showed you. But I'll show you that there's another reason that's more important that this is different too. And by the way, the part of the gains in stage 4 is that channel 37 becomes part of the TV guard band, and coordination with on the border with Mexico becomes easier. There's a whole bunch of stuff that went on that was also part of this story, but I'm going to leave those details aside. Okay, so we've seen this, this picture again. And again, the big deal that really made the cost fall is we needed so many fewer channels. This is, remember, 2 fewer channels. This is 1 fewer channel. This is 4 fewer channels. And that led to a drastic fall in the costs of clearing. Okay, so what are the consequences of this from the standpoint of efficiency? Yesterday, I described the efficiency of the auction holding the number of channels to be cleared fixed. But suppose that we have to go through multiple stages. We have to do something resembling Marshallian dynamics here. So in Marshallian dynamics, if a supplier exit when the quantity is high at the prices that prevail then, that supplier isn't missed when the quantity is decreased. Its early exit does not increase the total cost. Is that still true here? And I've given you some reason to think that in a knapsack problem it might not be true. How about here? How did sequential processing of multiple clearing targets affect the performance of the incentive auction? By the way, this is one of the few places, I'll say to Chris, where the FCC did not take our advice. We thought that it was silly for them to set the first and third clearing target. We thought that there's no competition at the first clearing target because they're buying as many licenses as possible. And the third clearing target, well, it took 4 more TV channels to clear 1 more block of spectrum. They would have been better off going from 9 to 7. So we thought that they had too many stages in this auction. They decided, well, let's clear as much spectrum as we can and keep trying for the higher amounts. But it's going to turn out that that was expensive. So we're going to take a look at performance, and we're going to measure performance using 3 criteria now. The first criteria that the government had in mind was the 3 criteria the government had in mind. First, the value of stations taken off the air. That is, we're going to buy some stations. These are stations that provided valuable programming. We want to minimize the value of the stations we take off the air. We want to minimize also the payments made to the stations. We want to keep costs low. And we want to maximize the number of channels that are successfully cleared. We'd like to clear a lot of spectrum for mobile broadband. So those were the 3 kind of performance criteria that I'll be reporting to see how everything worked. And in order to do this and understand how it worked in this particular auction, where the computations are bizarrely, enormously complicated, we needed to do some simulations. Now, we're not going to try to do any optimization here. So unlike the simulations I reported yesterday, these simulations are done with the whole US. And we simulate our auction and various variations around it. And that's what I will be reporting to you here. Okay, these simulation studies, these slides are borrowed and some are modified from ones by Kevin Leighton Brown. Kevin was the computer scientist that worked for Auctionomics on the designing well, the algorithms that we used and simulations that we ran. Okay, so the first thing you need to know about all of this is all this stuff that I'm reporting, including the simulations I'm reporting here, would not have been possible not long ago. This is a graph from Wikipedia, and this is just about transistor counts and what's happened from 1970 to 2019. And if you guys haven't seen a picture like this before, it's extraordinary, right? These are this is a log scale over here, so it's how many transistors we can put on a chip, and on a log scale, well, basically this thing has been growing exponentially for a long time, and we now have a lot more computing power. You know, in every few years we have a factor of 10 more computing power than we had before. And that was very important both for running the auction and also for these simulations that I'll show you how much computing power they took. Okay, so the simulation methodology, what I'm going to be reporting to you about simulations involves multiple steps. First of all, we have to build an auction simulator. Now, yesterday when I described the rules of the auction to you, I simplified a little bit. When we do a simulation, for theory, it helps to simplify a lot. When we do simulations, we try to be a little more realistic and include more of the detail of the auction, and I'll tell you about some of that detail as we go along. But you still have to choose the appropriate level of abstraction at which you're going to operate to do that, and so that's a step. The auction rules themselves are actually, the detailed rules are very complex. Okay, the second thing you have to do is you got bidders participating in the auction, you have to know what the bidders' values are. Now, of course, we don't know what the bidders' values are, but there were some publicly available data sets of researchers who had been trying to estimate what would happen in the auction, and they had made available to us their estimates of values, and we scaled them up and down to get some sense of what might happen, but we used the best publicly available data set to estimate what bidders' values could be. And some parameters feed into the bidder valuations, others specify how bidders will behave. It turned out that when we put in the valuations, we couldn't explain why some bidders participated in the auction and others didn't. So we created a model in which bidders whose values were higher than the opening price participated with some probability in order to match the actual participation rates. And so if you should have been willing to accept the opening price, then you participated with some probability. And if you shouldn't be willing to accept the opening price, you don't participate at all. So we created a participation model that way. And then we establish a probability distribution over model parameters. This is going to be a simulation, and so we used log normal distributions to multiply the parameters of the different stations to reflect the errors errors in measurement, and draw many samples from the distribution, and then we run paired simulations for any given set of simulated values and simulated participation. We talk about changes that we might have made in the rules and what effect they would have had on the auction outcome. So holding fixed the simulated values and the simulated participation decisions, we say if the auction had been run slightly differently, what would have happened in the auction according to that. So that's the basic simulation methodology. Everybody out there clear? Okay. And of course, we compare the outcomes. All right. So, and we're going to have 3 performance measures, as I've said. At the FCC, while the Democrats were in charge, the leading objective was how much spectrum would be cleared. That is, how many channels would be cleared for broadband use. That was the #1 thing they cared about when I was talking to them. They also cared, to a lesser extent, about the sum of the values of the stations removed from the air. Now, yesterday I didn't tell you about one of the features that got added to the auction. So our stations not only had the possibility of saying yes or no, that is staying on the air or going off the air. We also offered some of them the possibility of moving to a VHF band. So the spectrum they were on, which is perfect for digital broadcasting, is a UHF band. And the VHF band is a lower frequency band, which is less suitable for television. But they could say, well, we would accept, if you leave us on the air in the VHF band, we'll take that and we'll accept a smaller payment. So that was one of the options that was offered to the bidders during the course of the auction. So for stations that change bands, we had to we take a look at the loss of utility those bidders experience. And I actually described this to some of you. I don't know if I described this yesterday. Usually in computer science, when you measure efficiency, you take a look at the sum of the values of the things that are put in to the knapsack. And that turns out to not work very well here, because the stations that easily fit on the air tend to be much more valuable than the stations, and that's most of the stations, and the stations you take off the air, and you get this very big number in the denominator, and you get exaggerated measures of the efficiency of the algorithm. So we have a conservative measure determined in this way. And then the cost of acquiring spectrum, the sum of the amounts that's paid to the winning stations. Okay, so here we're going to leap into the simulations and talk about what we learned. Okay, and we're going to talk about 6 things. The first thing we're going to talk about is the multi-stage design. What did it cost us to go through a whole sequence of stages? All right, and these simulations are very expensive. The simulations that are reported here are almost 1,400 CPU days of computation to do just the simulations reported on this one graph. So these are very computationally intensive. And what we have here is what would have happened if we had started at the beginning knowing how much spectrum we were going to clear. We take 1 in value loss, what's the value of the stations that we have to take off the air, and 1 in terms of cost, and we call both of those things 1, and that's what we would have achieved if we knew in advance how many stations we were going to take off the air. Now, if this thing had gone through 2 stages or 3 stages or 4 stages, well, what we actually, if the whole thing had been done, I'm sorry, I said it backwards. What's up here is what the FCC did. It's the actual 4-stage procedure that we saw the FCC did. Had they guessed in advance how many stages there were going to be, that we were going to clear only 84 megahertz of spectrum, the normalized cost would have been on average about half of the cost that was incurred, and the loss of value from stations that were taken off the air would have been only about 62% of what it was. So we lost a lot by going through multiple stages. Okay, this was actually quite a big surprise that these numbers were this large. But it's very much like the story I told you about the knapsack problem. If you're putting things into a knapsack and you don't know the size of the knapsack in advance, and you fill your knapsack up with junk just because it's small enough to fit, then when the knapsack gets bigger, you can't take full advantage of the space that's being made available to you. Well, that's what was going on in this problem. If the knapsack was, if we knew how big the knapsack was going to be right from the beginning, we could have achieved much lower cost and much less loss of value. And here again is, if we didn't know exactly if we could have done the thing in 2 stages or 3 stages instead of 4 stages, we would, again, lose less than we lost going through the full 4 stages. So the advice that Auctionomics had given to the FCC was 2 stages. We thought that the first stage and the 3rd stage were wasted, and we weren't sure what they would do to the cost. And so our recommendation would have involved a 2 stages and would have saved considerably on both cost and value loss compared to the 4-stage auction that the FCC actually ran. Okay? By the way, only 2/3 of the value loss and half the cost if we could do it in one round. In terms of spectrum cleared, now here we had to vary the values that the buyers had, and we varied them from 1/3 to 2/3 to the full amount. I won't bother telling you about this one here, but we had to vary the values that the buyers had to see how much spectrum, how many stations might actually be cleared. And what we see is that when we're comparing one stage versus multiple stages, if the buyer values were very high so that we would actually clear in one stage, there's nothing lost. As the buyer values fall, one of the things that happens is we're going through multiple stages causes us to clear less spectrum. Now, the FCC's reason for having multiple stages was they hoped that would help them clear more spectrum. They thought that, well, you know, maybe we can get enough demand to clear 8 blocks. Maybe the cost will be low enough that we can clear 8 blocks and we'll have enough demand. Let's try it before we give up on that and go to 7. They didn't realize that they were increasing their costs so much by doing that they were causing themselves to clear fewer blocks than they would have otherwise. And what we see here is that the number of blocks that are cleared when the values aren't high enough to clear all of the spectrum are greater if we are able to reduce the number of stages that this goes through. Okay? And again, okay. Now, you know, things are always, in retrospect, are always a little easier to see than they were when we were planning. Here's an idea we didn't have before the auction, but we came up with after when we were going through this analysis. We said, you know, in the incentive auction, as it was actually run, what happened is the reverse auction was run first in each stage, and then the forward auction was run second. And we said, what if we did it in the other order? What if we ran the forward auction first and discovered there was only going to be $20 billion of revenue? And then we started running the reverse auction, and as soon as we found out that the cost was going to be more than $20 billion, we stopped. Didn't run it all the way up to $86 billion. We said, we're not going to be able to afford this anyway. Let's stop. Now, if you imagine that's sort of like doing the knapsack problem, in which I have a knapsack, and you say, you know what, I'm not going to be able to achieve my objective, so I won't fill up the last little holes in the knapsack. I'll stop when there's still plenty of space left in the knapsack. Then you're not going to make so many mistakes, was our idea. And when you're filling the knapsack, you'll be able to say, oh, actually, the knapsack should be bigger, and you'll be able to proceed in that way. So our idea was that if we ran the forward auction first and didn't run the reverse auction to completion until we could actually afford to clear the spectrum, we might avoid some of the mistakes that we make by this Marshallian dynamics approach. So the reverse auction the clock stops declining when its cost first exceeds the forward auction for the stations we're supposed to buy, given the revenue from that stage. Okay? So we're going to simplify the complex part. Well, what would that do? So here, you'll recall, this is a table you've seen before. Here's what the costs were. And the intuition that I'd like you to get is, well, in the first stage, it's obvious. You know, we have $23 billion in revenue. We have $86 billion in cost. We would have stopped the packing really early. We wouldn't have come anywhere near hitting any of the constraints that forced us to make stupid decisions in the first stage had we done that. And when we got to the second stage, it's 22 and 55. That's still pretty early stopping. And when we got to the third stage, it's 20 and 40. That's still pretty early stopping. We might have avoided a lot of the mistakes we thought, and this is a conjecture right now. I'm going to show you this conjecture is correct. But our conjecture was that had we simply reversed the order in which we ran the forward and reverse auction in each stage, we could have had better efficiency and lower costs. This doesn't happen in ordinary economics. Those of you who study ordinary convex economics, nothing like this happens in ordinary convex economics. The supply curves, demand curves, they all slope nicely. You don't have regret for that a station that you've rejected, at a high price, you might not reject. Those kinds of things don't happen. Okay, and I've described the intuition already in terms of packing a knapsack of unknown size. And what we decided to do was to see how good this would be. So the comparison that we're going to make is early stopping compared to using a perfect oracle. That is, if we stop as soon as we know that the costs are going to be higher than the revenues, how does that do compared to if we perfectly knew that it was going to take 4 stages? So the claim is that we should be able to eliminate nearly all of the errors just by the information we're getting out of the auction. That should be almost as good as having a perfect oracle that tells us that it's going to go 4 stages. This should be almost as good as running the auction in 1 stage. That was our intuition, and the results were confirming. What we found was that had we run the auction in reverse order, we would have come within 1% in both packing efficiency and cost of what we could have achieved with a perfect oracle telling us how many rounds we needed. So we missed this one. Was one of the innovations that we discovered after the auction, unfortunately. Okay, so one of the things that comes out of the simulation. Okay, and by the way, and the loss of spectrum from packing is 0. In all of the simulations we ran, if we used this, we did as well in terms of the amount of spectrum we cleared, which was the FCC's main objective, as if we had predicted perfectly what the maximum amount of spectrum to clear would be. Okay? Okay, that was the multi-stage design, what it cost us, and a variant multi-stage design, which in this actual auction would have performed a great deal better. The next thing I want to tell you about, since we're into simulations, is the consequences of allowing stations the VHF option. Now, we thought this might be quite valuable because these are stations that instead of having to buy, it's almost like having more channels available to pack them on the air. We pay them something and they move to a VHF station, and we don't have to pay the full price of buying the station. And so the real auction only reduced the amount of UHF spectrum available, but it repacked the UHF band, and it also repacked 2 VHF bands, the high VHF band and the low VHF band. And I won't get into the distinction between them, but it repacked 2 parts of the VHF band. And these are listed in more or less descending orders of desirability in the modern era. In the modern era, when we're doing digital broadcasting, UHF is best, high VHF is second, and low VHF is worst. And UHF stations may prefer moving to VHF rather than going off air. And some of the VHF stations might be willing to go off air to make room for UHF stations. So we allowed VHF stations to participate in the auction as well. And we had a pretty elegant design when we started. Adding this complicated the design, and in particular, it's no longer obviously strategy proof, and the method for keeping track of the price movements between the different bands, how we were going to decide for each band how to set the relative prices was very involved. I'm not going to go over those details here, but the actual auction involving the pricing of UHF and VHF bands was quite complicated. Okay? And was this extra complexity worth it? How much did we gain by selling VHF spectrum? So this is 101 CPU days. And what we're showing is a series of simulations, and all of these are paired. Okay? Every simulation is paired. And in every simulation, what we take in as the denominator, as the base, is what would happen with VHF. So the cost is normalized to 1, and the value lost is normalized to 1 when we include VHF. If we did not include VHF, So these things are all ratios to what would have happened with the same values if we did not include VHF, and the value is massive. You can see the star up here is at around 1.6 and around 2. The normalized cost without UHF would have been about twice as high, according to these simulations, and the value loss would have been about 60% larger, according to these calculations. So it turns out that including VHF was a vast improvement in the outcome of the auction. So I'm also trying to show you something about the collaboration between economists and computer scientists here. These are simulations I could never have run. The team of computer scientists with a lot of computing power, each of these simulations took hundreds of days of processing. Okay, on average, the UHF-only stations cost, the UHF-only auction cost more than twice as much and had a 63% higher value loss. Another thing that we talked about during the course of the auction was the opening prices. We have a descending price auction. How high should we start the prices? Now, yesterday when I talked about it, I didn't give you any hint as to how high, but the FCC decided that it was going to take advantage of greed, and it was going to put in some very high opening prices, so high that if you were a commercially owned station, you couldn't look your shareholders in the face and say, I'm not going to participate in this auction, because who knows what the price is going to be. And it might be, you know, the highest prices in the auction were on the order of $900 million, which is way more than any TV station is actually worth. So we started with these very high opening prices, and one of the questions was, did that affect the outcome of the auction? What would have happened if we had set the opening prices differently? And the answer is the opening prices hardly mattered at all. Running these things is another 400 CPU days. Every hypothesis we want to test is expensive in CPU time, but you can see that this spread is tiny. The normalized value loss, well, this is all on the order of less than 1%, and the normalized costs, the differences are all on the order of less than 1%. There's no difference. The opening prices can be as high as you like, and they do not affect, and you can see the range of opening prices is on a 6 to 1, and the difference in efficiency and auction cost is on the order of 1%. You can set these opening prices as high as you want, and if that encourages more participation, God bless, then you're in good shape, right? But it doesn't have any effect on the running of the auction. Okay. This is one that is in there because Kevin is so proud of it. The feasibility checker, the algorithms that were created for the auction, how important were they? What if we had run the same auction with when we're checking feasibility using commercial software? So up here somewhere, the state-of-the-art mixed integer programming software, which also does feasibility checking, are CPLEX and Gurobi. So CPLEX is somewhere up here, along with simple greedy algorithms. It would have led to normalized value losses about 3 times larger and costs about 3 times larger. It would have made an enormous difference if we had just used the off-the-shelf software. The Gurobi is better. It's 2.5 times as much cost and 2.5 times as much value loss. And Gurobi is the other state-of-the-art checker. And if you used special purpose SAT solvers, there are some that we found that would have done pretty well in the auction, PicoSat and this thing called G-Novelty plus PCL, God knows what that is. But you can see that these things are leading on the order of 50% extra cost or 25% extra cost and normalized value loss. The actual auction, which is in the software using the software that Kevin and his team created, saved a lot of money in this auction. Everything else cost a lot more. we're talking about costs on the order of $10 billion. So if you start adding 25, 50, or 150%, you're talking real money. Okay, this is, he was worth every penny we paid for him. So that's Kevin's software. Okay, at 342 computation days, right? Kevin likes to emphasize this is stuff we wouldn't, when things took 10 times longer or 100 times longer just a few years ago, this all would have been out of reach. Okay, now this is actually my favorite of the whole thing, and I'm sort of looking forward to telling you just a little bit about this one. Another rule that we put in place actually combined the economics and the computer science. So the computer science says, we're trying to solve these problems that are very hard, and during the course of the auction, we're processing the stations one at a time. And what will happen early on in the auction is if I'm processing Richard's station first, suppose that turns out to be hard and take a long time. Sometimes some of these things take a long time. Then everything else gets slowed down, and I'm not going to have very much time to process the other stations late in the auction. So how do we deal with that? So the first thing we do is we parallelize the process in the following way. We say each station is going to exit the auction at most once, or if it's frozen, if we're not going to lower its price, that's going to happen at most once. At every other round of the auction, they're going to say, yes, we'll take the price. And for some of them, at every round of the auction, they're going to say, yes, we take the price. But for all the other, everybody at most once gets either frozen or exits the auction. So most of the time, when you're checking whether a station can be feasibly added, the answer is going to be yes. So instead of processing the stations one at a time, what we'll do is we'll take, if these are the four gentlemen who are up next, I'll start processing Leonardo, and I'll start processing each of your stations, and I'll start processing your station as though the answer to his is going to be yes. And I'll start processing your station as the answer to both of those is going to be yes. And your station as if the answer to all three of those is going to be yes. And if they are yes, then I get a head start, and I save a lot of computation time. Now, the problem arises when one of these guys, Leonardo, ends up taking you guys finished, and you're sitting there, I finished processing you, but it turns out his station was the hardest to process, and it took me a long time to process his station. And at the end, he said, no. Now I have to restart all of you guys. And that could cause us to run out of time and do a poor job of processing. Now, as I explained to you yesterday when we went over the class of descending clock auctions, everything in this class is obviously strategy proof. So I don't have to process you in any particular order. And in fact, one of the things we can do, and this is the alternative strategy, is we simultaneously start processing for all the stations in parallel, and whichever one finishes first, we take. So suppose ITEC finishes first, then instead of restarting ITEC, because he took a long time, I say, I'm done. ITEC, I'm processing him next. And if he said yes, these things continue to run. And if you eventually say, no, I don't have to restart these stations because I've done the processing order in the order of speed. So the stations that are the easiest to process get processed first, and the stations that are hardest to process get processed last. I have the least amount of time lost to restarts, and at the end of the process, as timing is running out, and as I'm running out of processing time, I'm doing all the hardest problems in parallel at the end of the auction, at the end of the round of the auction. So that ends up making things work better. This is still a descending clock auction, so the obviously dominant strategy property is preserved. It requires more computers, in practice a few dozen. That's nothing in an auction like this. When it leaves time on the table, it means that no instance was solvable. It might be that it makes feasibility checking stronger. We don't know that his problem is always hard. It might be that maybe his problem is always hard, or maybe it's only hard if he comes in that position. We might be affecting the hardness of some of the problems. And it could be worse because it alters the bid processing order, and it might make no difference if the checker was strong enough. But we hypothesized that this would eliminate a lot of the time wasted in restarts. Idle processors, well, these guys are sitting around waiting to find out what happened to his station. So here's what we did, and this took 906 CPU days. As you can tell, this is a lot of processing power that is required to do these simulations. And here's what how the incentive auction, which the FCC ended up not implementing this rule, worked. And here's how it would have worked with the first to finish rule, where we had 1 hour of processing time in each round. And with 1 hour of processing time in each round, it saved a little bit. So it turns out it saves, simulations are especially expensive here. This is 906 days, and you don't see as many dots on this diagram as you've seen in other diagrams, because this is really an expensive simulation. So on average, we saved about 1% in a little more than 1% in cost, and we saved a little bit more than 1% in value loss by processing better. And the reason that this is so small, these are small numbers, I think the reason these are so small is that Kevin's algorithm worked so well that it was able to get most of the stuff done anyway. We think this is actually a considerable speed up in the processing and the auction, but the feasibility checking worked so well that we weren't able to add a lot of value in this way. Okay? Okay, so that basically is what we get out of the simulations. And again, I want to just say that the main message for today compared to yesterday, I was talking about the auction, just the reverse auction, clearing a fixed number of channels, and talking about the theory for how it worked and giving you a simulation for how well it worked with a fixed number of channels. With a variable number of channels to be cleared, the story becomes quite a bit more complicated. Our algorithm was motivated by Marshall's ideas, but we discover that in modern market design, Marshall's ideas don't work quite as perfectly as they do for a single homogeneous product. And the simulations give you an idea of which aspects of the design were important and which were less important. And that's it. Thank you.